This is problem 3 on practice exam 5 of chapter 1 in the book Problem Solving with Differential and Integral Calculus. We drop an object in the Earth's gravitational field. We're going to ignore air resistance. We're going to assume it's 10 meters per second each second. That's the gravitational field strength of the Earth. After 2 seconds, we can see it fell 20 meters. After 4 seconds, we can see it fell 80 meters. The normal equation that relates the distance it has fallen, y, to the time it has fallen, t, is this equation. So carefully draw a tangent line at t equals 2 seconds and get the slope. 2 seconds is right here. Let's identify the point. Let's draw a good tangent line. Now we have to get the slope of that tangent line. The run goes from 1 to 5. That's 4 seconds. The rise goes from 0 to 80. That's 80 meters. So the slope is the rise over the run, 80 meters in 4 seconds. The slope of the tangent line at 2 seconds is 20 meters per second, which is the speed after 2 seconds. On to part B. Do it at 4 seconds, the same thing. Identify the point, draw the tangent line, calculate the rise over the run. The run goes from 2 to 5 seconds. That's a 3-second run. The rise goes from 0 to 120 meters. The rise is 120 meters. The slope is 120 meters divided by 3 seconds, which is 40 meters per second. That's the speed at 4 seconds. And it should make sense because the acceleration due to gravity is 10 meters per second each second. If the speed is changing by 10 meters per second each second, after 4 seconds, it's going 40 meters per second. Let's do part C. Ooh, that's a big one. Part C, we're trying to wrap our heads around the average speed over a shorter and shorter interval. So we're starting at 4 seconds all the time. The initial position is always 80 meters. And then we're going to calculate the average speed from 4 to 5 seconds, from 4 to 4.5 seconds, from 4 to 4.25 seconds, ever decreasing intervals. And we're going to see what happens. So to start, we're going to get the position at the second time. We know the position at the first time is 80. What's the position at 5 seconds? And we can just use the normal equation for that. After 5 seconds, it has fallen a distance of 125 meters. And we stick that right here. After 4.5 seconds, we stick in 4.5 seconds into the normal equation. 101.25, that goes right here. At 4.25 seconds, it has fallen 90.3125. We stick that in. At 4.1 seconds, the total distance is 84.05 meters. After 4.01 seconds, it's 80.4005 meters. And at 4.001 seconds, the position is 80.04005. Now we're going to calculate the average speeds. What's the average speed from 4 to 5? We need the distance it has traveled from 4 to 5 divided by that time interval. To get the distance it has traveled from 4 to 5, we just subtract the two positions. So it's at 125 meters at 5 seconds, 80 meters at 4 seconds. The change in position is 45 meters. We divide that by the time interval, which is 1 second. The average speed is 45 meters per second. That goes right here. From 4 to 4.5 seconds, it falls 21.25 meters. Goes from 80 to 101.25. And the time interval is a half a second this time. And we get 42.5 for the average speed from 4 to 4.5 seconds. We stick that in. It fell 10.3125 meters from 4 to 4.25 seconds. The time interval is 1/4 second. The average speed from 4 to 4.25 seconds is 41.25. That goes here. From here to here, 4 to 4.1, it went 4.05 meters in an interval of 1/10 second. So the average speed is 40.5 meters per second. That goes here. In 1/100 of a second, it goes 0.4005 meters. The interval is 100th of a second. And we get an average speed of 40.05 meters per second. You should see what's happening here. If we go to a 1,000th of a second interval, it goes 4 centimeters. 4.0005 centimeters. The average speed over the interval is 40.005 meters per second. The smaller the interval, the closer the average speed is going to be 40 meters per second. This should make sense because we're getting closer and closer to the point. We measure the slope to be 40 meters per second at 4 seconds. If you use the calculus jargon, the limit of delta y over delta t at 4 seconds is 40 meters per second when delta t approaches 0. The smaller you make delta t, the closer the slope will be to 40 meters per second. And it's a good idea to add one more row to this table. Pick your own delta t. Smaller than 0.01. How close to 40 meters per second can you get? Take responsibility for your development. Don't just do what you're told. Explore for yourself. Don't say, thank God this problem's over. Say, do I really understand exactly what's going on here? If not, explore yourself. The goal is to really understand, not just do the work.